Okie dokie. So back to math. Anybody have any questions? Any homework questions y'all want to go over? Finish? Okay. You got time. No rush to do it today if you don't want to. You're not losing any points by doing it later or anything like that. So we good with the homework? It was spot on. Mhm.
No,
For this number here?
there's no choices. It's only the sample be
Yeah,
good,
that
learn
wasn't
more.
right. So let me see.
That's why I
These are
said,
what you got right. Mean, median, mode. Right. So you got like E right. So we're just missing B, C, D. Yeah.
yeah, that was wrong.
Yeah. Yeah.
Yeah.
That's all right. All right. So I'm just gonna assume from the silence that we good. All right. Let's look at what we're looking at today. So we're gonna be talking about binomial probabilities today. All right. So a binomial experiment. On a TV game show, each contestant has a try at the Wheel of Fortune. I don't know if y'all ever saw that TV show from back in the day. Right? I think the lady that does the Wheel of Fortune is still on the Wheel of Fortune. And she's been on Wheel of Fortune since I was a kid. You know, she don't age, man. That's a vampire. I'm telling y'all. Yeah, Vanna White. Yeah, that's a vampire. I'm telling y'all. All right. So anyway, in a TV game show, each contestant has a try at the Wheel of Fortune. The Wheel of Fortune is a roulette wheel with 36 slots, one of which is gold. If the ball lands in the gold slot, the contestant wins $50,000. No other slot pays. What is the probability that the game show will have to pay the fortune to three contestants out of 100 that play? All right. So in this problem, the contestant and the game show sponsors are concerned about only two outcomes from the Wheel of Fortune. The ball lands on the gold, and then they have to pay out the $50,000, or the ball does not land on the gold, right? And then they don't have to pay nothing, right? This problem is typical of an entire class of problems that are characterized by the feature that there are exactly two possible outcomes for each trial of interest. These problems are called binomial experiments or Bernoulli experiments, right? After the Swiss mathematician Jacob Bernoulli, all right, who studied that in the 60s. Good for him. So, features of a binomial experiment. One, there's a fixed number of trials. We denote this number, excuse me, by letter N, right? Sample size, it's our sample size, right? The N trials are independent and repeated under identical conditions. Step three, each trial has only two outcomes, success denoted by S and failure denoted by F, right? Step four, for each individual trial, the probability of success is the same. We denote the probability of success by P and that of failure by Q. So the probability of failure is Q, right? Since each trial results in either success or failure, success plus failure equals one, right? Remember, the sum of all the probabilities must add up to one, right? And also, the complement is true as well. The probability of failure, Q, is equal to one minus the probability of success, right? Which is P. So Q equals one minus P. This right here is on your formula sheet. Q equals one minus P. The central problem of a binomial experiment is to find the probability of R. R is the number of successes out of N trials. Okay? So here's an example. Let's see how the Wheel of Fortune problem meets the criteria of a binomial experiment. We'll take the criteria one at a time. All right? So, number one, each of the 100 contestants has a trial or a try at the wheel. So there are n equals 100 trials in this problem, right? So that's one reason why it meets the criteria. Two, we assume that the wheel is fair, right? So the trials are independent. Everybody gets their own spin, right? Since the result of one spin on the wheel has no effect on the result of another spin, right? Three, we're interested in only two outcomes on each spin of the wheel. The ball either lands on the gold or it does not. So let's call landing on the gold success because they won $50,000, and not landing on the gold failure because they didn't win nothing. All right. In general, the assignment of the terms success and failure to outcomes does not imply good or bad results. These terms are assigned simply for the user's convenience. All right. So what they're trying to say is you could run a binomial experiment where you're looking for something that in English terms would be considered bad, right? But in mathematical terms, that's your success. Let me see, give you an example. Let's say uh I don't want to pick anything too gruesome. All right, here's an idea. Here's an idea. Let's say that you go to the supermarket, right? And then you're trying to buy a dozen eggs, right? Um, None of y'all should be buying eggs though, because y'all got the pantry downstairs giving it out for free. Just saying, right? But anyway, right? Let's just assume that like we bougie and we go into the supermarket and we buying a dozen eggs, right? Now, let's say that the farm that the eggs is coming from, every now and again it makes a mistake, right? Instead of you getting like 12 regular eggs, maybe like every once in a while a fertilized egg comes in, right? So that like there's like a legit baby chicken one of the eggs. But you don't want that. You want eggs to eat, right? So that could be like that could be considered a failure, right? Like having the baby chick in the egg. That's not what you want. You want like a plain egg so that you could have your bacon, egg, and cheese or whatever, you know? So if you were running a binomial experiment, success could be you finding the baby egg, you know? So like it's I'm trying to say that like the roles could be flipped, but they're just titles, they're just names. So they're not actually success and failure in English terms. That's what I'm trying to say. All right. So let's get back to this, right? On each trial, the probability of success landing on the goal is 1 out of 36. So it's 36 slots, one of them are gold, right? Since there are 36 slots, right, and only one of them is gold, consequently, the probability of failure, Q, is equal to 1 minus P, which is 1 minus 1 over 36, which is 35 out of 36. So if you land on one of them other slots, you get nothing. There's 35 of them that you could land on. We want to know the probability of three successes, right? So three people landing on the gold out of 100 people that try to spin that wheel, right? So R is equal to 3 in this example. It turns out that the probability the quiz show will have to pay the fortune out to three contestants out of 100 is about 0.23, right? Later, we're going to see how you can actually compute that. Okay. I'll leave that up there in case anybody want to copy. Well, this is going to get real cool real soon. All right. So anytime we make selections from a population without replacement, so we don't put it back, right? We do not have independent trials. However, replacement is often not practical. If the number of trials is quite small with respect to the population, we almost have independent trials, and we could say the situation is closely approximated by a binomial experiment. For instance, suppose we select 20 tuition bills at random from a collection of 10,000 bills issued at one college and observe if each bill is in error or not. If 600 of the 10,000 bills are in error, then the probability that the first one selected is in error is 600 out of 10,000, or 0.06. If the first is in error, then the probability that the second is in error is 599 divided by 9,999, or 0.0599. Even if the first 19 bills selected are in error, the probability of the 20th is also 581 over 9,981, or 0.0582. All of these probabilities round off to 0.06, and we could say that the independence condition is approximately satisfied, right? So the sample is so large that even though I'm taking out from the population, right? And the population is dropping along with the success number, right? I'm not really changing the probability of the event happening, right? It's just that the size is so large, you know? Law of large numbers right there. So next we're going to see how to compute the probability of R successes out of n trials when we have a binomial experiment. So we're going to look at this in a couple of ways. All right. See that sound right there? That's what make me sleep good at night. Anytime I hear a siren, I know I'm good. You know? When it be too silent, I'll be like, yo, what's going on outside? I don't know. Something going on. Excuse me. For real though, like I hope nothing serious is happening, like with that siren. Sometimes I hope they just turn the siren on to beat traffic, get past the traffic light. That made me happy. All right, computing probabilities for a binomial experiment using the binomial distribution formula. Not gonna lie, this gonna be intense. All right, let's take a look. The central problem of a binomial experiment is finding the probability of R successes out of n trials. Now, we'll see how to find these probabilities. Suppose you are taking a timed final exam. You have three multiple choice questions left to do. Each question has four suggested answers, and only one of the answers is correct. Right? We all been here before, right? Right? SATs, all of that. All right. Anyway, you have only 5 seconds left to do these three questions. So you decide to mark the answers on the answer sheet without even reading the question. So we just trying not to leave it blank, right? Assuming that your answers are randomly selected, what is the probability that you will get 0, 1, 2, or all three questions right? Let's talk about it, right? So successes, you get the question right. Failures, you get the question wrong, right? So this is a binomial experiment. Each question can be thought of as a trial, or there are n equals 3 trials. The possible outcomes on each trial are success, S, indicating a correct response, or failure, F, meaning the wrong answer. The trials are independent. The outcome of any one trial does not affect the outcome of the other. What is the probability of success on any one question? Since you are guessing, and there are four answers from which to select, the probability of a correct answer is 0.25, right? So one out of the four choices that you have is correct, right? And three out of the four choices that are there are wrong. That's it, right? So the probability of failure, Q, on the wrong answer is 0.75. And sure, we have a binomial experiment. N is equal to three questions. P, your probability of success is 0.25. Q, your probability of failure is 0.75. Now, what's the possible outcomes in terms of success or failure for these three trials? Let's use a notation SSF to mean success on the first, success on the second, and failure on the third. There are 8 possible combinations of S's and F's, and here they are, right? So sorry about that. These abbreviations that you see up here, right? These are all the possible outcomes that could happen with those three questions, right? SSS is what you want, right? That means that you got all three questions correct, right? SSF, that's not too bad. You got the first two questions right. You got the third one wrong, right? SFS, not too bad either. You got the first one right, second one wrong, third one right? So on and so forth. What we don't want is we don't want that FFF, right? We don't want to get all three of them wrong, right? So to compute the probability of each outcome, we can use the multiplication law because the trials are independent. For instance, the probability of success on the first two questions and failure on the last is the probability of SSF, which is the probability of the first question right, times the probability of the second question right, times the probability of the third question wrong, right? And again, the probability of success we know is just 0.25 times 0.25, and then the probability of failure is 0.75. Multiply them all together, you get 0.047. In a similar fashion, we can compute the probability of each of the 8 outcomes, right? So let me show y'all what that's going to look like in a table. The table is going to make it a lot easier. So this is the likelihood of each of the 8 events occurring, right? So with n trials, so we have the SSS, which we want all 3 questions correct, right? That's just going to be 0.25 times 0.25 times 0.25, which when you do it on the calculator comes out to 0.016. Simple, right? SSF, right? That's like you getting 2 questions right, 1 question wrong, right? That's 0.047 when you do it out on the calculator. Each event, you're just multiplying it to one another, right? Remember also, I don't know if I said this earlier, but anytime you have two variables next to each other, they're just next to each other, in between them is the word and. You remember and means multiply. That's why I'm multiplying them, right? Excuse me. All right. Now we have this one, which is me getting 1 question right. So that's a 0.141. And then we have a 0.422 chance of getting nothing right. Damn, it really doesn't pay to guess, you know? So now we compute the probabilities of R successes out of 3 trials for R equals 0, 1, 2, 3. Let's compute the probability of 1. So the notation, probability of 1, stands for the probability of 1 success for 3 trials. So there are 3 different outcomes, right? You can see that from the chart here. There are 3 different ways that we could have 1 question right. It could be the first question right, the next 2 wrong, the first one wrong, the second one right, the third one wrong, or it could be the first 2 wrong and the last one right? So you want to know what's the probability of you just getting 1 question right. So what do you do with those 3 numbers? You just add them up because it's right on one or right on the other or right on the other one. right? So we just add those. Boom, right? So that's how you get the 0.4222, right? That's the probability of you getting one question right out of the three of them. Now, this is looking a little bit better for our guessing, if you ask me, right? Because to me, that looks like I have a 42% chance off of just raw guessing with those three questions of getting at least one of them right. That's not too bad. That's to me, that's a gamble worth taking. You know, imagine you was playing basketball and that was your free throw percentage. You'd be a beast. You know, Jalen Brunson don't have that percentage. You know? This is the example right here. Yeah, the Wheel of Fortune. Yeah, we just breaking it down thoroughly though. That's why.
I mean, that's the operation
Mhm.
to do.
Yeah,
Or
but this is, to be honest with you, this is a really complicated way of me explaining it. But I want you to know where this is coming from. But I am going to give you a really, really, really simple formula that you could just use that'll just work, and you don't have to do all of this out. But I want you to see like how to think through the problem, you know, how to understand what's going on with it. So this is another table. This table is displaying the probability of you getting no questions right, one question right, two question right, three question right. The difference between this table and the previous one is going situation by situation, outcome by outcome. But in this table, I'm condensing them. This is just by R. You get no questions right, you get one question right. I don't care what order you get it right in, right? Two questions right or all three right. So bam, right? Looking at this now, this makes me think a little bit differently. I have a 0.422 chance. I have a 42% chance of getting at least one question right. Right? Well, no, let me say that again. No, let me rephrase that. At most, excuse me. I have a 42% chance of getting at most one question right. I would take my chance and guess on those three questions, right? Because I have two options on the test, right? Either I'm gonna leave them three questions blank, they're gonna be wrong anyway, right? Or I'm gonna guess on those three questions and maybe I get something right. But what this is telling me is that I have a 42% chance of getting one of those questions right off of guessing, you know? So you should definitely guess on a multiple choice test. All right. Since we talking about guessing on tests though, right? Let's say this is real life. This is you now. This is all y'all now, right? Y'all taking a multiple choice test, right? A, B, C, D is the answer. What you guessing? We don't know the question. We don't even know what the answers say, but what you guessing between A, B, C, D, and E? No, A, B, C, D. I'm sorry. You gonna go with C? All right. All right. What about you? What you gonna guess? Which one? A? All right. All right. All right. Anybody else? You want to test? You got questions through four answers A, B, C, D. What you guessing? A? It's true.
I get randomly
Mm-hmm.
or for a.
Mm-hmm. Okay.
Does that mean because it says the chances I would say, right? But the chances of going back, it's as to the chance of taking one letter, it goes straight down.
I agree with that. Yeah. It's a little bit more complicated because when you randomize it like that, like now you're introducing more randomness into the answer. Maybe it is right, maybe it isn't wrong. It is wrong, you know? It's like a guess of a guess now, you
Yeah.
know? I wanna I wanna like minimize my Probability of failure, in other words. Yeah, I would do that. Yeah, I agree with that. Yeah. Well, which letter would that be? Would it be A for you? Okay. Anybody else?
No, mean, everybody you more likely to get it.
You're more likely to get something than nothing. You know?
If I'm told a lot,
Yeah.
see.
Okay. Okay.
What would the
All right.
answer start B or D?
There's no answer. So I'm the question I'm posing to you, right, is you could choose whatever you want. You don't know the question. You don't even know what the answers say. You just have four choices to choose from: A, B, C, or D. What you gonna choose?
D?
Okay. Okay. But for sure, nobody's choosing D, right? Dang. All right. If it was me though, right? And I had A, B, C, or D, right? My choice would be either between B or C. More likely than not, it would actually be B, right? Now, when we get deeper into the class, right, we're going to learn something called normal distribution, right? Where most of your answers tend to be in the middle. So more people are going to choose the middle answer than the outliers. A and D are outliers. So more likely than not, that's not the answer. It's probably going to be one of the middle answers. You know? So B or C. You know? So next time y'all on y'all test, y'all don't know the answer, just choose a middle answer. And that's it. You know? It worked for me in high school, I ain't gonna lie. Mhm. All right. We have done quite a bit of work to determine your chances of R equals 0, 1, 2, or 3 successes on three multiple choice questions. If you are just guessing, now we can see that there's a small chance, about 0.016, that you will get them all correct. All right. So this table can be used as a model for computing the probability of R successes out of only three trials. But how can we compute the probability of 7 successes out of 10 trials, right? We could develop a table for n equals 10, but this would be a tremendous task. But there are 1,024 possible combinations of successes and failures on 10 trials, right? So now, at first, we did the quiz, but we just didn't know the last three questions. So now we're trying to guess on the whole thing. 10 questions. Damn, you know, that's hard. Fortunately, mathematicians have given us a direct formula to compute the probability of our successes for any number of trials. Let's take a look. This is going to be fire. Make y'all powerful after today's class. Right? I'll make you go to English class and ask for multiple choice test after this. All right. So, formula for the binomial probability distribution. The probability of R is equal to n factorial over R factorial times n minus R factorial times your probability of success P raised to the R power times your probability of failure Q raised to the n minus R power. Also written as n choose R times P to the R power times Q to the n minus R power. Cool, right? Where n is your binomial trials, that's your sample size. P is your probability of success on each trial. Q is your probability of failure on the trial. And remember, Q is a complement of success. So it's 1 minus success equals probability of failure. Excuse me. R is the random variable representing the number of successes out of n trials, right? So R is how much success you're looking for. R has to be between 0 and n, right? Always. R is between 0 and n. The factorial, that's what this exclamation mark here is, right? Factorial notation is n factorial. It designates the product of all integers between 1 and n. So, for example, 4 factorial is equal to 4 times 3 times 2 times 1, right? Special cases are 1 factorial, which is equal to 1, and 0 factorial, which is equal to 1 as well, right? So let's do an example of that. Let's say that I ask you for 2 factorial, right? Start with the number 2, and you're just going to go down. So this is just 2 times 1, right? If I said 3 factorial, start with the number 3 and then go down. This is just 3 times 2 times 1, etc. That's what a factorial is, right? You just count down from whatever the number is, and then you end at 1 when you're multiplying each one of them together. All right? Putting that all together, we have what's called our combination formula here, right? So combination is n choose r. That's n factorial over r factorial times n minus r factorial. This is our binomial coefficient, right? So this gives values for n choose r for select n and r. Many calculators have a key designation for n choose r that gives the value of n choose r directly. If we're breaking down this formula piece by piece, right? You already know that for any one particular outcome is going to be the probability of success times the probability of failure, right? And raised to the power of the number of successes. So what's the points of the combination there, n choose r? Remember when we were doing our previous question where we tried to figure out the probability of you getting one question right on the test, right? And then you had 3 questions in total, right? You saw that there was multiple ways that we could get one question right on the test. Maybe it's the first question right, the next 2 wrong, or maybe it's the first one wrong, the second one right, the last one wrong, or maybe it's the first 2 wrong and the last one right, right? But which order do you get them in? That's the purpose of the combination formula. It's taking into account the different ways that we can get one question right. All right. So not too bad. I want to show you guys something. One second. Just gonna have to bear with me one second. So I do have some good news. This formula is on your formula sheet. So you Mhm. Yeah, that's all I need for every question. That's the easy way. Well, the rest of that was just explanation on what that meant, you know? So right here, where it says binomial probability distribution, this is your formula right here. You don't have to memorize it. It's right there on your formula sheet in chapter 6, right? And in case you forget what's n, what's r, right above it, it tells you r equals the number of successes. P is the probability of success. Q is equal to 1 minus whatever P is, right? Which is the probability of failure, right? All you got to do is just plug it into the formula, click enter, write the answer down, and you're good for the question. That's it. Copy and paste. Mhm. Literally for your homework, that's all you got to do. Plug in the little numbers, click enter, write the answer in, hit submit, go to the next question. All right. So please note the binomial coefficient n choose r represents the number of combinations of n distinct objects, where n is equal to the number of trials in this case, taken from r at a time when r is equal to the number of successes. So for more information, you can look that up. All right, so let's look more carefully at the formula for the probability of r. There are two main parts. The expression probability of success raised to the r times probability of failure raised to n minus r is the probability of getting one outcome with r successes and n minus r failures. The binomial coefficient n choose r counts the number of outcomes that have r successes and n minus r failures. For instance, in the case of n is equal to 3 trials, we saw from the table 6, 8 that the probability of getting an outcome with one success and two failures was the probability of success p raised to the 1 power times the probability of failure raised to the 2 power, right? Where r is equal to 1, n is equal to 3. We also observed that there were 3 outcomes with one success and 2 failures. So it was 3 choose 1, which is equal to 3 when you do the math on it. All right. Not expecting you guys to do the math on that because y'all have calculators, but I'll show y'all how to do it. This is a typical question that you will see. Excuse me. So it says compute the probability of R using the binomial distribution formula. So privacy is a concern for many users of the internet. One survey showed that 59% of internet users are somewhat concerned about the confidentiality of their email. Based on this information, what is the probability that for a random sample of 10 internet users, 6 are concerned about the privacy of their email? All right. So let's check this out. So we have 59% of internet users are concerned. Let's leave it at that. We have a random sample of 10, and we want to know the likelihood that 6 are concerned. All right. So let's look at what we have. We have a probability of success. Success in this case is you being concerned about the privacy of your email of 59%. This could also be written as 0.59 as well. So we have a sample size n of 10 internet users, and we want to know r equals 6, right? So essentially, we want to know what is the probability of 6 people being concerned about their internet. Remember, we have our formula, right? Our formula is probability of r is equal to n choose r times our probability of success raised to the r power times our probability of failure, which is 1 minus p raised to the n minus r power. Literally just plug in the numbers and you're done. That's it. Right? So my n is what? 10. Choose r, which is 6, times my probability of success, which is, I'm going to say 0.59, raised to my number of successes, which is 6, times 1 minus the 0.59, raised to the 10 minus 6 power. Nothing crazy there, right? Can everybody do this? Copy down a formula and then copy down the right variable in number to where it belongs?
Well, okay, Bond, you're confused.
What are you confused about? This I copied from the formula sheet.
Right.
These I copied from the question
Okay.
in yellow. And this, I just plugged them all in. Is that doable?
The 10 is from the N
Mm-hmm.
and the radius 6,
Mm-hmm.
and then 59 from the, alright, 59 for 6,
Mm-hmm.
and then 0.1, 0,
Mm-hmm.
from where you, that number 1 there, from where.
This? It's the probability of failure.
Oh,
All right. Um, if I'm looking at my formula sheet, you see this says N choose R times the probability of success raised to the R power times Q. You look up, Q is right here, it's just 1 minus P. That's where I got that from.
do you have a formula sheet like, because that is not in the yellow?
It is.
It is?
It is. Hmm? Yep. Literally, whenever you guys are doing a test or anything in this class, the answers are all on the formula sheet. You just have to copy. With the formula sheet? Oh, I'm sorry. Oh, like you were copying the question, you mean?
Yeah.
I got you. Okay. Now, after you get this far, you could just type it in the calculator and click enter, right? But I'm gonna show y'all a little bit of how to do it by hand, just to show you how deep you could go with it, and to convince you to use the calculator, because I know some people in here is against the calculator. So 10 choose 6. This is 10 factorial over 6 factorial times 10 minus 6 factorial. It's gonna be a decimal. Yeah. Every answer that I get is always a decimal. The probability answers. This is 59 over 100 raised to the 6th power times this one, which is, what's this, 41 over 100 raised to the 4th power. All right?
See?
Mm-hmm. Yeah.
Like NCR.
NCR. Mm-hmm.
So, see there?
Combination. Yeah. Nah, it becomes the next thing, the factorial thing that you saw that I just wrote down with the exclamation marks. Like this is what C turns into. This thing. Go ahead. 10 minus 6 is 4, yeah. Yeah. Go ahead. The six is your number of successes.
We did NCR. We did NC6.
Yeah.
How you said it? 10 exclamation point.
Yeah.
This means 10, 10, 10.
Yeah.
Well, what happens to 6?
I'll show you. It gets deeper.
We're already past it. Doesn't we?
The 6? We didn't pass the 6 yet. Yeah. I'm gonna show you. So you know that the factorial means 10 times 9 times 8 times 7, right? So literally that's what I'm gonna write down. It's 10 times 9 times 8 times 7 times 6 factorial. And I'm gonna stop right there. On the bottom, 10 minus 6, you know, is what? It's 4, right? So then this is just gonna be what? 4 times 3 times 2 times 1 times, I'm just gonna put 6 factorial here. You know why I'm doing that, right? Yeah, I'm about to do this. I'm about to cancel that joint out. Boom. Make my life easy, right? The rest of this, I'm not even going to touch this because I'm not going to lie to you. The calculator is going to do this part. Because that's 59 to the 6th power, which is 59 times 59, 59, 59, you know? And that's 100 to the 6th power, which is 100 times 100 times 100, you know? I probably could do the 100 to the 6th power, but I'm just going to save my brain power right now. Y'all know I got to go to work after this. All right? Yeah. If you just do the numerator and then the denominator, yeah. Yeah. So then another way you could simplify this, just cancel out the bottom with the top. 4 goes into 4 once, 4 goes into 8 two times. 3 goes into 3 once, 3 goes into 9 three times, 2 goes into 2 once, 2 goes into 10 5 times, right? So what do we have? We got 5 times 3 times 2 times 7 times 59 over 100 to the 6 times 41 over 100 to the 4th. Little calculator, boom, and you get the answer. All right. Questions on this? No copy from the top? All right. I'm just showing y'all how to break it down. For me, on my test, right? It is, right? Yeah. That's why I want y'all to use a calculator. You know? For me, on my test, I'm cool if you go from right here. You see what's this probability of 6 equals this? If you go from this to the final answer, I'm cool with that. But if you against the calculator, this is how you go step by step through everything. You type it in a calculator, click enter.
Oh, if we type that in,
Yeah,
it'll give us the answer, like,
exactly.
and then you each time, following.
Exactly. All right. Hmm? So,
I know my question about
How do the seat?
I'll show you. Yeah, go ahead.
it. You see how
Uh-huh.
and should always be a bigger value.
Always.
Yes.
Always remember that. Yeah. And should always be bigger because that's your sample size. Yeah. R could be equal to N, but R can't be bigger than N. Mhm. All right, that was a good question. So let me show y'all how I would do this now. Do. 1 second. Gotta scroll down to the problem. So I'll just type it in the same way I have it written on there. All right. So 5 times 3 times 2 times 7, right? Times open parentheses, you already know, right? I'm about to do that 59 divided by 100. Close parentheses. I'm going to raise that to the 6th power. Use the arrow, get out of that power, times. Open parentheses, I'm going to do that 41 divided by 100. Close parentheses, and I want to raise that to the 4th power. Let's see what I get. Bam. So I got 0.25030342245. Yes, your 36X Pros can do this as well, all right? But there's a reason why I'm using this big calculator, right? I have an even easier method that I'm going to show you guys right now, in case y'all don't want to go through all of this. All right? But my other calculator don't have it. I have to use the big one for that. Go ahead. Hmm? If I'm what? Nah, I have more to talk about, but go ahead. What's your question?
Well, yeah.
Um, for the bottom, oh, it canceled out. So 4, you know that 4 times 2 is 8. So 4 goes into 4 once, 4 goes into 8 2 times. So that's how I got the 2 up here.
Minus 6 equals to the 10 minus 6. Then you have explanation, and then 6 explanation, maybe no explanation. Then shouldn't it be? I don't really know.
Because the 6 exclamation and the 6 exclamation on top and bottom, they're gonna cancel out. Because you know what those are. Those are just 6 times 5 times 4 times 3 2 times 1, right? When whatever you divide on the top by the bottom is just 1. It's the same thing. So that's why I just cancel it out. And I'm trying to make my life easy. That's why, you know. It was there because that the numerator is 10 9 8 7 6. Right. I just didn't continue the 6 because I knew that the 6 on the bottom was gonna kill it, you know? So that was my trick right there. But let me show y'all another way that you guys can do this. All right. Now y'all could verify that this is right because I got the right answer right there. Right? Let's just recap real quick. Our N is what again? 10. My probability of success was what again? 59%, right? And then my R was 6, right? All right. So let's say that you wanted to do this question, probability of 6, but you want to use the calculator to do it. This is how you do it in the calculator. Right? You're going to go to binomial PDF. And then you're just going to write in your numbers. You have to remember this formula though. This is binomial PDF of NPR. Right? So in our case, for our question, N was 10. Probability of success was 59% or 0.59. And my number of successes was 6. You could type that straight in the calculator and get the answer. But how do you find it in the calculator? All right. Those of you that got the TI 36X Pro, I'm gonna talk y'all way through it, right? Right? So the first thing you want to do, you want to hit second, then you want to hit the data button, right? So second and data. After you hit second and data, you're gonna go across, you're gonna use the right arrow.
Where, second.
This is not you, not you, not you, not you.
Second and
Alright.
data,
Yeah, second and then data.
then
And then you want to use the across arrow like this, right? You want to go to where it says distribution, DISTR. All right. If you have the TI-83, all you have to do is press second and then distribution, DISTR. All right. Once you're here, you're going to go down to where it says binomial PDF right here. You're going to click enter. They're going to ask you for a number of trials. Remember, trials is your N, right? In our case, our N was what? It was 10, right? Then they're going to ask you for your probability of success. In our case, our probability of success was 0.59. You can also put 59 divided by 100 if you're not sure, right? Your X value is your R, right? That's your number of successes. In this case, it was what? 6. Then you just press enter, enter. Did I get the same answer? All right. Same thing, right? 0.250303 for 245. Right? This is how you do it in the calculator. Your choice, you got options. All right. Y'all want to do it by hand? Do it by hand. Y'all want to do it in a calculator? Do it in the calculator. All right. You can practice this on your homework. All right. Y'all already know I don't like rounding, so just write everything else on. Just press enter. You got the same thing as me? Yeah. You got the same answer?
I didn't, that they'll just following.
Did you go down to binomial PDF?
I don't know exactly how it is.
Let me see. All right, start over.
Okay.
Go to
Second,
data.
right here.
Go across the distribution. Not down, across. Not up, across. Like to the right. Go to the right. All right, now go down to binomial PDF.
Then enter.
Enter. Enter again. Now enter your trials. You can copy from the board. Right, your N was 10. Let me go across here so you can see. N is 10. And N is your trials also. Remember that?
Just can't, yeah. And then just can't 59.
Huh?
Oh,
59%, or you can write 0.59. Or you can do 59 divided by 100, whatever.
like that.
That's the 59. The trial is your N, right? Trial is 10. Just 10. Nothing else there.
So how supposed to type it? 10?
Oh, 10 enter. That's how you write 10. 10 enter. Like type it. 10 enter. And then for the success, 0.59. Enter. And then for your X or your R value, 6. So 6 and then enter. And enter again. Did you get the same answer?
Oh, very good.
0.2508.
425.
Good. And that's it. Mhm. All right, all right. So now, so second distribution, right? And then you're gonna go down to binomial PDF. Yeah.
Oh, once you put second distribution into the count.
Yeah, then you go down there. Yours is different though, because you don't have the GUI. So you have to remember that formula up top, NPR, right? So then you're gonna type in 10 and then comma, right? This is the comma right here. And then the 0.59, and then
Then
the comma again. Then 6,
Then 6.
right? And then close parentheses and then enter.
And that's the answer.
Yeah.
So then the first step will be hitting this second.
Yeah. And then the distribution. This thing in yellow.
Okay.
Yeah.
So, okay.
You're welcome. All right, those of you doing your homework, I'm sure you guys encountered this problem already, so let's talk about it. I know y'all about to ask the question. So, using a binomial distribution table, all right? Now, in many cases, we will be interested in the probability of a range of successes, right? In such cases, we need to use the addition rule for mutually exclusive events. For instance, for n equals 6 and a probability equal of success equal to 0.5, what's the probability of 4 or fewer successes? That is, what's the probability of R less than or equal to 4? So that's the probability of 4, 3, 2, 1, 0, all of them together, added up, right? But you see, everything we just did right there, we just found the probability of one event, the probability of 6. For this question, we got to do the probability of 4, 3, 2, 1, and 0 and add up all of those together. So we have to do like multiple steps right there. So it would be a bit of a chore to use the binomial distribution formula to compute all the required probabilities, right? Table 2 of the appendix gives us values for the probability of R for selected p-values and values of n through 20. To use the table, find the appropriate section for n, and then use the entries in the columns headed by the probability values and the rows headed by the R values. All right? Let me show y'all something. Just to recap, right? I want to know the probability of R less than or equal to 4, which is going to be the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0, right? And like I said, the last question we did, all we did was just 6, so we got to do it individually for each one. But what I want to do is I want to use a table to do that. So in this question, sorry, in this question, my n is equal to 6 and my probability of success is equal to 0.5. But I have an easy way to deal with this. All right. Easy way to do this would be just to look at the formula sheet. So let's take a look at the formula sheet for a second. All right. So looking at my formula sheet, right, I can go to my binomial distribution tables, which is right here. This is called table 2. Literally just turn the page and there it is. All right. So if I was going to use this, right, remember I have three things. I have my N, my P, my R. My N in this case is 6. So here's my N's. You see where I have this little 2 to 3 to 4? I'm going down to 6. This is N6. So this is where I want to be in this column, this bracket of numbers, right? Up top, these are my probability of successes, right? We said that my probability of success for this question was 0.50, so here we go. All right. Now, scrolling down here, 0.16, right? So this column right here, right below the 0.16 that you see right here, these are all my probabilities, right? These are the numbers that I'm looking for, right? So the first one, 0.16, this is the probability of 0. The probability of 1 is 0.094. The probability of 2 is 0.234, etc. These are the answers all in this column. You're just going to write them down and then add them up, and that's the end of the question right there. All right? Now, this is the formula sheet. I have a prettier version I want to show you guys to get my numbers from. Just bear with me 1 second. Here we go. So this is a little bit of a zoomed in version from the table that we just got, right? Probability of success is 0.50, N is 6, and here goes all my numbers right here. All you have to do is just copy them down, add them together, and that's it, right? So the probability of 4 is 0.234. Let's write that in. Plus the probability of 3, that's 312. What's the probability of 2? That's 234. Plus 1, that's 0.094. Plus 0, 0.016. On your calculator, just click add between them, and that's it. All right. Questions on this?
Is that multiplication just?
No, add.
4 plus?
Add.
That means add.
Yeah.
That's it.
Mhm.
I raise my hand because the attention.
Oh yeah. Just grab one of these. Here, just let me borrow your pen real quick.
Yeah.
Just get the date real quick. There you go. Now I can just sign real quick. Anyway, right? Let me just do this real quick in my calculator. $1.34 you got? Okay. I got 0.89. Each one of these is a decimal, by the way. So it's like 0.234, 0.321. And at the end, there's zeros in front. So this is like 0.94 and 0.16 at the end. Yeah. Yeah.
And we have
Yeah.
to put it exactly like it, in the, like that, 0.234, so it's point.
Yeah. Or you could say 0.234 if you want. That's fine too. Yeah. That's fine. Yeah. So that's one way that you could do this, right? Now, let's talk about it. This table excerpt from table 2 of the appendix shows the section for n equals 6. Notice that all possible R values between 0 and 6 are given as row headers. The value of P equals 0.50 is one of the column headers for n equals 6, and the probability of 0.5. You can find the value of the probability of 4 by looking at the entry in the row headed by 4 and the column headed by 0.5. Notice that the probability of 4 is equal to 0.234. All right. Real quick. I'm gonna take like 2 minutes real quick. There's a way that you can actually do this in a calculator. All right. Let me show you. Just to recap. N is equal to 10. Probability of success. Wait, is it 10? Hold on. I'm sorry. N is equal to 6. Sorry about that. Probability of success is 0.5, right? And let's say that I want to look for R less than or equal to 4, right? So I'm looking for this. I want the probability of R less than or equal to 4, which means the probability of 4 plus the probability of 3 plus the probability of 2 plus the probability of 1 plus the probability of 0, right? That's what I'm looking for. So if you wanted to do this in the calculator, you would simply go to binomial, OMAL, CDF. That's the second one that you saw in there in the calculator, right? So real quick, the probability of R less than or equal to some number is equal to binomial CDF of NPR, right?
Do you know what you say right now?
It's a different formula. It's a different formula. Yeah. So for this one, our N is 6. Our probability of success is 0.5. And our R in this case was 4. Typing it in the calculator real quick. I'm gonna take just a quick second just to show y'all. So real quick second. All right. So you go to your distribution, right? If you're in the 36X Pro, first you got to go second, data, then go across the distribution and go down, right? You're trying to look for something called binomial CDF, right? Click on the binomial CDF. They're going to ask you for your trials. Once again, trials is your N, which is 6 in this case. Our probability of success is 0.5. And then my X value in this case is the 4. So when you do the CDF, remember that's going to be all 4 numbers added up, right? So that's the probability of 4, 3, 2, 1, 0 added up. So here we go. Here's our answer. It's 0.890625. Right? So let's make this page a little bit bigger so we can take a look. No problem. Just to compare our answers, when we did our table, we got 0.89. We did the calculator. We also got 0.89 as well. Same thing. All right. All right. Let's call it for today. All right. See y'all tomorrow. Homework is posted if you guys want to try out what we learned today. All right. Tutoring is open. I'm on my way over there now if you guys want to join me. All right. See you soon.